Hi students, in this first video, we are going to talk about some of the basic principle fundamentals of chemistry, mostly our measurements and our calculations. So what is chemistry? Well, it's a science for the 21st century. Originally, its definition is the study of matter and the changes it undergoes. But really, we want to take a different look at that. We want to take a critical look at the interaction with energy. We are going to have a chapter with thermodynamics and how we can get energy and the transfer from one source to another based off of what matter can do. Now, many people will talk about chemistry and say how difficult it really is, and it is one of the central sciences, but we are not in this business alone. Many times people will ask, well, what about physics and biology and engineering? Well, in a small sort of way, physics is chemistry in motion. We are going to talk about massless objects. We have to create that matter in order for us to get motion that we see in physics. What about biology? Well, it's really chemistry in a cell, but it's seen in a larger micro scale sort of way. We are going to talk about atoms bonding to other atoms, but really what biology and biochemistry is large scale arrangements of those atoms all working to help with the benefit of a living organism. Finally, we talk about engineering. Engineering is a core science and has shown this over the past 20 to 30 years, but really where its applications of chemistry are what separate it from the other core sciences. So we're going to come up with the theories, but really engineering becomes the application and being able to include and build something to help us with the processes that we're going to go forward with. So why study chemistry? Well, there's a lot of reasons why. If you're going into the medical field, you need to understand how those atoms are going to work. If you're going to go into the engineering field, you want to know somehow your basic raw materials are going to work. And really, you cannot escape chemistry in a normal day. So where's the difficulty? In our language. The language that chemists use is inevitably harder. We use very descriptive terms. We will sometimes use similar terms for different things, or we will use multiple terms for the same thing. Being able to understand those terms and the language that we are going to use them in the context is going to make this much, much easier. As you see here, we have three terms that really get thrown around all the time: theory, skeptic, organic. Those are terms that were actually taken from us and used in modern day society. So what does it mean to be a skeptic? You hear that today in today's society. Well, it's actually a good thing. Being a skeptic means that you see the data for both sides of an argument, and you historically will side with the one with the more proven data and the one with the larger amount of data. That's a good thing. But as you've heard in many times, being skeptical of something means that you are unsure of it, when it's actually the reverse of that. You have seen both sides. You have both sides sitting in front of you, and you have gone with the ways of the data. And we could talk about organic. You walk down your aisles of your grocery store and you see organic bread or organic milk and organic and organic and organic. What does that mean? Normally, to many of us, that just means that it's $2 or $3 more expensive, and that it may not have such things as GMOs in it. But to a scientist, organic means it's made of carbon and hydrogen and maybe some nitrogen and oxygen. So we use the term organic much more liberally and much more broad. And now in the main environment of the world, we've gone and used that much more rigid in saying, oh, this is how this was made, and so on and so forth. The nice part about all of this is you guys are all chemists. Cooking is considered chemistry, following directions to build something. But really where chemists make their money and where they are so useful towards society is problem solving, problem solving, problem solving. Given an idea of what could be wrong and solving it is where people get paid. So it's nice that when you're cooking, you can go and read the directions from the back of the box and produce brownies. But the best brownies have something a little bit more in it. Those are problem solvers. Yes, we could go and do a simple surgery and we could follow that to the T, and we would hopefully get a good result in which someone is healthy. but the best doctors are problem solvers. So that is what most of this course is going to focus on. Can you problem solve, and how do I make your problem solving skills better? But let's talk about another challenge, and that is the consistency in reporting results. As many of you have seen, not only in a media or polling sort of era, especially that in social media, it's consistency of reporting results. How can we know that the data that we are getting is true? The best way that we can look at it is that we need to repeat it, and it is going to be based off of units that are easily understood. So let's talk a little bit about some problem solving tips, and I'm going to highlight some movies that are very classical in my upbringing to help you guys understand this. So let's look at the first one. I was elected to lead, not to read. Now, some of you are going to think that that may be our current presidential situation, but that's not at all true. This is actually the president based off of Arnold Schwarzenegger in the Simpsons movie. Reason why I bring this up is you want to read the problem fully, and you want to label variables, not just skim for numbers. It has actually been shown in chemical education studies that students will look to the numbers and then start to randomly place the possible relationship with those numbers. So we may have problems with 3 or 4 numbers, and you're just looking at maybe adding, subtracting, dividing, who knows what. How about we label them, look at what we have, and most of the times, the equation that you're wanting to use will self-identify itself. So one of the things I will really recommend for you, and you will see when I work some of the problems, I will label all of my variables. What about equations, tables, and unit analysis? These are typically what I call the scary 3. Well, what are the scary 3? The scary 3 are the ones that students are most terrified about when getting to chemistry. How do I use equations? What does this data in this table mean? I don't like using units. What I'm going to tell you is that they're actually a safety net for you. Let's use those tools that you're given, but be expected to be given less than you think. What happens if I don't give you that equation? Well, if you do number 1 correctly and you identify, you might say, hey, I've got pressure, volume, temperature. Hey, I've got stuff for the ideal gas equation. If all of a sudden I start to give you numbers and an equation, you may be able to figure out the units. It's really, really critical that you take all of the data, not just selected parts that you think that are important. Will I give you sometimes extra data that you don't need? Absolutely. But at least at that point, you can look at it, say you don't need it, and put it off to the side. Most problems come from an underutilization of the data instead of an overutilization. Give me a minute, I'm good. Give me an hour, I'm great. You give me 6 months, I'm unbeatable. This comes from Hannibal Smith from the A-Team. I grew up watching the TV show, and of course there is the movie where this line comes from, but it really talks about taking time to solve a problem. Historically, most mistakes are made on speed, but we have to worry about this duality, and I want you to see this is how our course is built. I want you to learn at a snail's pace. Label everything. Make sure you get the pattern down. Walk before you can run. But really what you didn't know is there's even a step before that. You had to crawl before you could walk. So what does that mean? Get the process down. These are what those videos are for. I am going to go at a snail's pace when I am solving all the problems in this video. Then when we get to the problem sessions in the Zoom meetings in which we will meet, I will speed up some. As you're starting to go through the quizzes, you'll speed up once again. And finally, when you get to the exams, you're going to have to work as fast and as diligently as you know how. So it's going to be this evolution of start slow. Are you speeding up? Are you speeding up? There will become a point to when you speed up will become a detriment to your problem solving abilities. We want to stop there. There is no point in going faster if you're going to get it wrong. But there's also no point to going super slow because then you won't get to all of the problems. We are going to work on that for you throughout this entirety of the course. And finally, is your answer reasonable? How many times have you asked a question to a family member and they give you an answer that makes no sense? You would say, hey, Mom, what's for dinner? Tuesday. What in the heck does that mean? And we laugh about that, but there will be times that you produce answers like that for me on an exam. I might ask for an answer in mass, and next thing you know, you're giving it to me in moles. You've not answered the question. So as we start to go and build very systematic ways of answering problems, you have to look at your answer and say, is it reasonable? If I ask for a sample of carbon and you say that it is 845 kilograms of carbon, does that make sense? Well, probably not. 846 kilograms of carbon is almost 1,700 pounds of carbon. I don't think they're going to let us do that in the lab. Maybe you have made a mistake in your math and it's just maybe 846 grams of carbon. We really need to work on that because most wrong answers can be found easily. But if you don't know what you're doing, there's a problem. So as you can see here, we have the line, students don't know what they don't know. So what does that mean? Well, that's what we talk about self-efficacy. Do you know what you should be learning? This is going to be an evolutionary change for you for your academic setting. You're going to be able to look at a problem and say, I don't know this, but I can work through this. We want to get us to go from there to saying, hey, I feel confident doing this. It's very easy when I explain problems because I have 15 years of experience. For you, for some of you, this may be brand new or a year or two of experience at a much different level. So now we have to say, does this seem like a good answer? We'll get to that. So finally, we can now get to how we build important measurements. Well, first things first, you have to know what you're studying. If I'm going to use length, I might use a meter stick or a ruler. If I'm doing volume, especially in chemistry, I might use a graduated cylinder. But am I going to use graduated cylinders if I have a swimming pool? Well, absolutely not. I would use something like gallons. When it comes to mass, I may use a balance. But do you want to know how many grams you weigh when you get on a scale every morning? No, we do stuff when it comes to weight, which is a mathematical conversion. Temperature, you have a thermometer. But we also know that there are 3 different temperature scales that will highlight which one are we going to use. Every measurement that you have from these days forward must contain 2 parts, a number and a unit. The number tells you the quantity. The unit tells you the size. So I might say that I have 10 toes. 10 is the number. Toes is my unit. If I were to sit there and say I have 10 legs, you would probably sit there and say either the number is wrong, I have 2, or maybe my unit is wrong. I'm not talking about legs. Maybe I am talking about fingers and toes. So it's very, very important. One way we can get around this, or one way we can discuss this, is let's talk about running. If you run every morning, you become healthy. But I might tell you, I run 2. Well, Dr. Collins, what does that? I run 2 feet from my bed to my couch, and that's my day. Technically, I said I ran. Well, what does that mean to somebody who runs 2 miles? So the number is critical because it tells us the quantity, but we need to know the value associated with the unit because feet and miles is a big difference of 5,280. So as you can see, we had to come up with a standard, and that is the SI units. This is created by the General Conference of Weight and Measurements. These are the standards, the international standards, and the ones that we are going to use predominantly as our basis set. For all SI units, we are going to have 2 major parts. The base unit, what we are studying, and the prefix. The prefix is going to tell us the size of that. So let's go ahead and look at some of our base quantities. As you can see, for length, we have the meter. Mass is actually the kilogram. It's not the gram. So one of the things that's interesting about mass is it already comes preloaded in its standard unit with a prefix, the kilo prefix. We are not going to do stuff in the lab at the kilogram scale, so we are actually going to use the gram. So while mass might be the standard at the kilogram, we are going to use the gram because it is just much more usable for us. You can see the second is going to be for time. Thermodynamic temperature is Kelvin. We have our amount of substance for mole. And really, we don't use electrical current all that much until we get to general chemistry 2 with the ampere. and our luminous intensity we tried to hold off for our physics friends. So now you can see here are listed all of our SI prefixes. Historically, when we are wanting to learn exactly what we are doing, we want to go between tetra and our femto. You are expected to know between those groups. So now when it says tetra, I also want you to go and make a slight change. This is based off of a British setting. It's not tetra, but tera. You've heard this before when it comes to terabyte used for our computer value. So in English speech, tetra is a correct usage, but we actually prefer it just to be tera. So let's start from really small and go to very big. So femto is very important now when we are starting to deal with the wavelengths or the size and masses of some of our subatomic particles. As our technology gets better and we are able to study that stuff that is smaller and smaller and smaller, femto is being used more and more and more. Pico, you've probably heard of picometers. So now you can see that we're starting to get a little bit bigger. Nano is a little bit bigger than pico. You're going to hear things from nanometers. You're going to see stuff that is going to have a possible volume of nanoliters. That could be the volume of an atom or a molecule. Then we go to microliters. This is typically the first tangible volume that you will see that you can physically look at. Having microliters, that may be a small drop when dealing with an individual measurement. Then we go to milli, probably best known for the milliliter, which we know is the cubic centimeter. So a milli is 1/1000th of a liter. So it's really important for us to have that as we're starting to go through. Then we get to centi, which is centimeter. That means that there's 100. And then deci is 1/10. So now let's go to the ones that are larger than the base unit. So we have deca, which is 10. So if we have a decameter, that is 10 meters. Then I can go to hecta, which is an H. So that is 10 to the second. Then we get to the kilo. So that's 10 to the third. So if we're talking about kilometers, that's 1,000 meters. Then we can go to mega, which is 10 to the 6th. We start to see this now when we're looking at megabytes, dealing with computer processing storage speed. But if we had an Xbox that had megabytes, that's not nearly as good. What about an Xbox or an iPhone or an iPad with gigabytes? Well, that's what we typically have now, something that either has 256 gigs, as we've started to shorten it over the last little bit. But now that we've started to see for many Xboxes and all of our newer computers, we're now to our terabytes, which is actually 1,000 gigabytes. So as you can see, you need to be able to go through and look at all of these as well as be able to convert from one to another. So let's try a few examples for this as we're starting to go through. So let's convert the SI units that I have now to the target unit with the prefix. I will show you two ways on how to do this. The first thing we want to do is go and take our 42.83 centimeters and go to millimeters. So what I can do is go through our base unit. So if I have 42.83 centimeters, the first thing I can do is go and take that to meters. So what I want to do is take our non-base unit and give it the exponent. So we know that in many cases, we want to talk about 1 centimeter. Well, what is that? That is going to be 10 to the minus 2 meters. Notice that my non-standard unit gets the 1, while my base unit gets the exponent. So then if I want to go to millimeters, I now have to look at this as 1 millimeter is 10 to the minus 3rd meters. Now, I think we can all agree that our 10 to the 2nd and 10 to the 3rd are going to cancel out in some ways mathematically, but really what this process is going to be these two values together are actually just going to be times 10. So if I look at my millimeters, I would end up with 428.3 millimeters. So you can go and combine our conversion factors, or if you're a little bit leery, go through the base unit and take it to the second unit from there. Either way is completely acceptable. So let's go ahead and try B and C, and that will finish us up for this video. So let's go and try with B. I've got 6.01 grams, and I want to go to kilograms. So how do I do that? Well, if I do that, I can go and say for my 1 kilogram is going to be 10 to the third grams. So this means that my grams and grams will cancel, and I'm going to be left with a value of 6.01 times 10 to the minus third kilograms. So notice that as my unit gets bigger, my number gets smaller. This is critical for us as we are starting to worry about our calculations. So let us go to C. Notice that I have 0.125 meters, and I'd like to go to centimeters. So that means that I need to put centimeters on top and meters to cancel on the bottom. So based off of this, I need to have 1 centimeter is going to be what? Well, that is 10 to the minus 2 meters. So notice that my value and my unit are going to go in opposite directions. My unit is getting smaller. That means that my number will get bigger. So what does that mean? I will get 12.5 centimeters. So as you could see in this video, numbers, data, the language are truly and incredibly important. As you're working through the remainder of these examples on your own, make sure to see if it does make logical sense. If your unit gets bigger, your number should get smaller. If your unit gets smaller, your number should get bigger. We are going to use this basic set of science understanding and our units and our numbers for the entirety of the course. Make sure that you are practicing these as we are starting to go along. In our next set of videos, we are going to continue to talk about our data, not only about our fundamental units, but how we can come up with our logical answers. Have a great day.